We're going to try these three improper integrals now. They should look very familiar. They're the same three that we just did in the last video, where p equals 1, p equals 2, and p equals 1/2. But the bounds don't go from 1 to infinity, they go from 0 to 1. So if the bound doesn't have infinity in it, then how can it be improper? Well, as you've probably noticed, 0 is not part of the domain of any of these functions, so there's going to be a vertical asymptote on each one of these graphs. So we're going to have to replace 0 with a variable and let that variable approach 0 from the right. So if we look at the graph here, I have the other side of that vertical line shaded as well. Last time we just had this area over here. We've dealt with the blue, remember that was infinite, the red, that was also infinite, and the purple, which was only 1. Now we're going to deal with the other side of this. So let's focus on just the original one. Okay, so we did get this one. Now we're going to get this one, right? This region between 0 and 1. All right, good. So let's see how that works. We are going to replace 0 with a and let a approach 0 from the right. So the limit is a approaches 0 from the right of the integral of a to 1 of 1 over x dx. Same integral as before, so the antiderivative is going to be the same. We have the natural log of a minus the natural, nope, we're going to start with 1, aren't we? The natural log of 1 minus the natural log of a. Well, the natural log of 1 is 0, and we're going to let a approach 0 from the right. And if we recall, the natural log function, well, we talked about how it grows without bound as we go to the right, slowly, but without bound. Well, if we go to the left, then it shrinks without bound very quickly, right? It shoots down to negative infinity here. So as the argument of the natural log function approaches 0 from the right, the output becomes negative infinity. So we say 0 minus negative infinity, because this approaches negative infinity. Well, 0 minus negative is positive infinity. So this integral diverges. Okay? All right, so that might be unsurprising. Okay? In fact, I hope it's not surprising at all if we consider the fact that the graph of 1 over x is symmetric with respect to the line y equals x, we can note that its inverse is itself, right? The inverse of 1 over x is 1 over x. So this region above the line y equals x is exactly the same shape as this region to the right of, did I say y equals x? Y equals 1. This region above y equals 1 is exactly the same shape as this region to the right of x equals 1. So, and again, that's because these guys are inverses of each other, and there's that reflective property there. Okay, so so not a surprise at all. But let's take a look at 1 over x squared. Remember that the area to the right of x equals 1 was finite; it equaled 1. Whereas now we're trying to figure out the area over here. Notice how, while it has a vertical asymptote at x equals 0, it doesn't seem to approach x equals 0 quite as quickly as it approaches y equals 0, right? So that's kind of an informal thing to consider. In fact, if we look at this line, it's hopefully clear that there's not reflective symmetry here, right? The inverse of 1 over x squared is not 1 over x squared. So let's go ahead and jump into this and see what happens. We're doing purple on this one, I think. So we'll take the limit as a approaches 0 from the right of the integral from a to 1 of x to the negative 2 dx. And we already did that, right? That was negative 1 over x was the integral, so we'll evaluate negative 1 over x at 1 and at a, factor out the negative 1, and get 1 over 1 minus 1 over a. Now last time we were letting b approach infinity in the denominator, and that went to 0. This time we're letting the denominator approach 0, and 1 over 0 is infinite. So we have negative 1 minus a negative infinity, or 1 plus infinity, which is infinite. So this one also diverges, all right? And you might actually notice that these guys are inverses of each other, right? So the inverse of 1 over x squared is 1 over the square root of x. So it shouldn't be surprising if you think about that this region right here approaches the asymptote just about as quickly, in fact, exactly as quickly, as this one approaches the horizontal asymptote, right? These guys are inverses of each other, and in fact, if we look at the line y equals x, we can see that the two graphs are in fact reflections of each other over that line. All right, so that must mean that if the purple region converges to the right of x equals 1, then the blue region must converge over here, right, to the left of x equals 1. All right, so let's see if the analytics bear that out. We'll go ahead and see what happens in our blue integral if we evaluate this improper integral. Again, we're going to let a approach 0 from the right, and we've got a to 1 of x to the negative 1/2 dx. And remember, we already did this before. We got 2 times the square root of x, so we'll factor out the 2. Let the limit approach 0 from the right. We'll evaluate the square root of 1 minus the square root of a. Oh, well, wait a second. The square root of a is just 0. So we just get 1 minus 0, or 2 times 1 minus 0, which is 2. So this integral converges, which is not surprising, but what perhaps is surprising is that the converging value is 2 instead of 1. I'll let you guys think about why that might be the case. A graph will really help you on that. Why would the purple region to the right of x equals 1 equal 1, but the blue region to the left of x equals 1 be equal to 2 if the shapes are the same size? All right. So pay attention to this region right here, and hopefully you can answer that question yourself.